Okay. So now, given this, what are we essentially saying is that at the sampling edge of the clock, there has to be a duration for which data remains stable. Beyond that, data can actually be anything. Similarly, after the clock edge comes, there is some duration for which data is not stable. Output is not stable. But then output becomes stable after that. Are you able to see this? And are you also able to see, Raghav, you're asking about contamination delay. Are you also able to see the definition of contamination delay here?
So I mean, after the contamination delay, I can see some changes in the output.
Yes.
So, but
Already output has started to change.
but now why I'm not considering that as a stable kind of thing? I mean,
Because it is not stable yet.
so because if I take this as the shortest delay, so as the shortest delays happen and my data is stable now, then I mean, I'm
Okay. Let
taking
us
the
consider
propagation
a
as
case.
stable.
Let us consider the case of a 8-bit register.
Okay.
So there are 8 flops.
Yes, sir.
For this 8-bit register, the outputs will start to become variable after the contamination delay.
I mean, yes, sir. I mean, yes.
And they will become stable only after propagation delay. Are you with me?
So
After the propagation delay, see, one flop in the register was to transmit a 0, another flop was to transmit a 1, and so on. So the zeros ones, the ones that had to transmit a 0, they may transmit it a little earlier. So they define the TCCQ. The ones that had to transmit a 1, they might be doing it a little later. So they define the TPCQ. Finally, when is the output stable, 8-bit output stable? Only after TPCQ.
so this is the most pessimistic worst case scenario I'm considering. After this, anyway, how that my data would be stable.
Yes. So what do you want to consider?
Worst case. So, but there could be a case that after the contamination, also my data could be stable, but I will not consider that as the word. I will consider
Because you're
propagation.
doing a sign off, no? You don't want
Yes.
things to fail on silicon.
Okay. Yeah. Okay, sir. Got it, sir. Thank you.
Okay. Yeah. So now if you wish to characterize these setup and hold times, what do? What you do is you start. So there is this clock edge. You say that I will start to bring my data close to the clock edge. And as I do that, you will notice that my output delay would increase a bit due to change in output slope. Okay. And when this output delay, say, increases by 5%, it becomes 1.05 times of the, the minimum delay that you could observe. That is what you call as setup time. Okay. Now, exactly the same way, for the other edge of data also, you will notice that as you start to bring the hold edge closer to the Q pin, to the CK transition, the C to Q delay will again increase. Okay. And again, we say that 5% increase, that is where the hold time is. Let us look at in a little detail. Let us say we have this setup, this kind of a, let us say, latch. This is a latch. Right? So what do? We say that there is this clock edge, the sampling edge of the clock, because we are talking about a latch. There is this clock edge and data is toggling. I will start to bring data closer to the sampling edge. And now I want to see what is the TCQ. As I bring it closer and closer, TCQ you will see would increase. Okay. As TCQ increases, all the timing assumptions start to go haywire. So we say that the point at which my TCQ has increased by, let us say, 5%, that is my setup time. Similarly, for the same latch, there's this hold thing that we're talking about. I bring the transition closer to the clock edge again, and you will see again TCQ is changing. So we say that wherever this is more than, again, say 5%, that is my hold time.
Sir, is this 5% standard or it can change from?
It can be different from one company to another, from one technology to another, and all that. So don't consider 5% as a standard, but in our course we will consider 5%.
Sir, sir, whatever people put in their papers like setup and hold times, don't they follow a certain criteria like this 5% rule?
So they will tell it in their paper.
Okay.
They will tell it in their paper how they have measured. Okay.
So
Yes. Devjit, you're asking something?
Yes, sir. Sir, I wanted to ask that above this 5%, the points are still plotted. So I can say that flop is still working, but this is like a safety limit, right?
Yeah, it is still working, but the timings have gone so high that your system would fail. We'll see. Now we will do the timing closure part. Okay, you've done. So when you will do the VDF course, you will see that there is a setup time, the STA that we have to do. We discussed this in the first lecture of DVD also. We want to ensure that all the flip-flops, every circuit has appropriate setup time. If you give a clock which is faster than the minimum period that the synthesis run tells you, your system can fail. So we will just see the timing closure part, and you will see that if this timing increases further, then all your systems can fail. We don't want to do that. Therefore, we say 5% is what we want to keep. Okay.
Sir,
Yes, Faisal.
so when we are when we are changing the not changing, when we are making closer the data to the clock pulse, the clock to Q delay is increasing.
Yes.
So why is that happening? I'm not able to visualize it.
Okay. So when the data is toggled much later than clock, what happens? Whatever D was there, it remained stable after this transmission gate became opaque. It changed.
So can you please repeat the statement?
Let us say that data toggled much after the sampling edge.
Yes, sir.
So in that case, what was happening? This D1 was very stable.
Yes, sir.
When these transmission gates, the NMOS and PMOS were turning off, at that point of time, this gate was very stable. Am I right?
Yes, sir. Yes, sir.
The input was very stable, and therefore the CK to Q delay was something.
Yes, sir.
Now, as I bring my data edge closer to the clock edge, what happens? ये ऐसे delay होता जाएगा. This will delay, and
Yes,
this
sir.
will no longer be stable.
Huh.
So what can happen? There can be a disturbance which can move on to the other side.
Yes, sir. Yes, sir.
What does that disturbance do? That disturbance actually degrades the slope of the transition over here on the second side.
Okay. Okay. Yes, sir. Yes, sir.
Therefore, if you measure at, say, 50% transition,
yes, sir,
the delay would change. Are you able to see this?
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. So now that we are clear about setup and hold time and how they are to be measured, let's look at how is this timing, how are these timings signed off on the system level. Okay. So we'll look at sequencing timing constraints now. What does this mean? This means that if there is a combinational path between two flip-flops, what is the minimum clock period that I can give? Huh? Or if I'm using two-phase latches, there is a positive edge level triggered latch and there is a negative level triggered latch, or there are two phase transition latches, so I have two clocks. Okay, then what kind of combinational logic can I put in the two regions there? Huh? What kind of combinational delay can I put in those regions there? Or as I'm missing out on who mentioned about the pulsed latches. If I create a very short pulse over here, then how much combinational delay can be put over here again? Are you able to see this? So whenever we are designing a sequential circuit, we want to find out what is the fastest at which my system can run. Am I right? And that fastest could be different for a regular flip-flop based architecture or a two-phase latch-based architecture or pulse latch-based architectures. Are you able to see this?
Yes, sir. Sir, but this if we are able to make the pulse latches, that is fine. But why don't we use them? Because they are smaller as well.
So they are used. Who says they're not used?
Okay. So I thought that flip-flops are more preferred since sometimes
Yeah.
there is warning even in synthesize when we
We will
synthesize
see.
the
We will
latches.
see why pulse latches have problems and why flip-flops are better. That we can see. That is not a problem. But pulse latches are used.
They are flexible also, sir. Like the timing is kind of
So they
more
are
flexible.
used. They're very widely used. Well, widely, matlab, in some kind of design and in some parts of the industry, they are very widely used. Not everywhere, because there could be some reasons, and we will look into those reasons. But yeah, they are used. That is why we are discussing them over here, na?
Yes, sir.
So a quick recap of the different delays. We will now, call logic propagation delays as TPD and TCD, propagation and contamination delays as TPD and TPCD. The clock-based propagation delays as propagation C2Q and contamination C2Q. Latch would also have propagation delay from data to Q and clock and from contamination delay from D to Q. And for latches and flops, we will also have these timings called setup and hold. All of these we will consider when we talk about sign off abhi, thoda sa late delay mein. Okay.
Sir,
Yes.
so what do you mean exactly by sequencing? Was the term sequencing? What do you mean by that?
No. Okay. What do you understand?
So, like,
We discussed this in the first part of the sequential circuits section. So what do you understand by sequencing?
so is it like related to pipelining?
Can be said that. Yeah.
I mean, how I put my combinational part, a combinational part between the flip flops, and that is basically the sequencing thing.
Yeah.
See, and sir, I had a doubt regarding the two-phase pulse latched implementation. So can you move to the previous slide?
We will talk about two-phase pulse latches in much detail abhi aage
Okay.
jaake. But yeah,
Okay.
please.
Okay. So I mean, I understand the flip-flop implementation. So sir, with respect to these two-phase pulse latches, sir, I can see that this what I need is that from the sampling edge, my data should be available to be stable data available. So all these time for which my clock period is high, that basically is not is basically I don't want that, right? I want my, why would I consider my clock should be, I don't want the clock to be high for a very long time, right? Because
Depends. We will see. This is not a default assumption that you can make. We will see there is a benefit of having a pulse width.
okay.
Hmm?
So actually I was not able to clarify, understand that why we are, what
Yeah. We
exactly.
will see. We will see in a little. We will
Okay,
want to do some time borrowing, and then we will need this.
okay, sir. Okay.